So you're working late, running a massive spreadsheet, and you grab your laptop charger. It is physically burning hot to the touch. Or imagine accidentally leaving your phone in the sun while running GPS. The hardware physically can't take the heat. It gives you that temperature warning and just forcibly shuts down to save its own life. Now, take that heat and scale it up. Imagine a warehouse the size of 3 football fields, packed floor to ceiling with the most powerful computer processors ever built. Hundreds of thousands of chips running simultaneously, 24 hours a day, training the next generation of artificial intelligence. Warm is the understatement of the century. It is a thermodynamic nightmare. The heat generated by modern AI is catastrophic. Tech companies are pumping millions of gallons of purified drinking water through the walls just to keep the buildings from melting down. They are literally looking into building dedicated nuclear reactors just to power the air conditioning. I am completely serious. We are hitting a physical wall. Artificial intelligence is growing exponentially, but the hardware is trapped by the laws of physics. But what if we just stopped using electricity to compute entirely? We are officially ditching the electron. We are talking about breaking down a monumental breakthrough in physics. In April 2026, researchers figured out how to build computer chips that process AI data not with electrical currents, but with pure light. We are talking about computing with lasers, way beyond just fiber optics. We are talking about Frankenstein quasi-particles, picosecond switching, and completely eliminating the heat problem of modern AI. Before we compute with lasers, why is electricity failing us? For 80 years, we've used electrons to process data, and it worked. The electron has been the absolute, undisputed king of the information age. Every text, every photo, every game is the result of electrons moving through microscopic wires inside a chip. So what is the problem? The electron is getting tired. Or rather, it's getting too crowded. At its core, a computer is just billions of tiny microscopic switches called transistors. They flip on, or they flip off. A 1 or a 0. Binary code. And to flip those switches, you have to physically move electrons from point A to point B. But here is the fundamental physics problem. Electrons have mass. They are incredibly tiny, but they are physical objects. They have physical mass, and they carry an electrical charge, which means they take up physical space. When they move through material like copper or silicon, they bump into the atoms. They create friction. In physics, we call this electrical resistance. And as everyone knows, friction creates heat. Think of a computer chip like a logistics network. You have millions of tiny delivery trucks, electrons, moving data across a city. But the roads have friction. The trucks cause traffic, they bump into each other, they idle, and they generate massive exhaust. When you're just typing a Word document, there's not much traffic. The trucks are moving fine. But training large language models is like demanding those trucks move a billion packages simultaneously, millions of times a second. It is absolute gridlock. The friction gets so intense that the chip physically cannot dissipate the heat fast enough. The energy required to cool the chips now frequently exceeds the energy required to actually run the math. The bottleneck for AI isn't the software. The software is brilliant. The bottleneck is thermodynamics, heat. If we want AI to advance, we need a delivery truck with zero mass, zero charge that moves at the speed of light. Enter the photon, the fundamental particle of light. They have zero rest mass, they have zero electrical charge, they don't experience electrical resistance, and they travel at 186,000 miles per second, as fast as the universe allows. We already use light to move data. Fiber optics run under the oceans connecting continents without generating heat. So if we already know how to move data with light, why aren't our computer chips doing the actual math with light? Because of the flashlight problem. If you shine 2 beams of light at each other, what happens? They just pass right through. The beams don't crash, they don't interact. Because photons have no mass and no charge, they are completely antisocial ghosts. And that's a problem. Computation requires logic gates. It requires a signal to bump into another signal to make a decision. If they pass right through each other, there is no interaction, no logic gate. No logic gate, no computer. So current chips use a clunky conversion process. They catch the light, translate it to electricity, do the math, and translate it back. It's like flying a supersonic jet across the Atlantic, but then forcing everyone to ride bicycles for the last mile. To build a true, all-optical AI chip, you have to somehow force light to interact with itself. Make photons crash. For decades, it was impossible. Until April 2026, researchers at UPenn created a masterpiece of quantum engineering. The short answer is, If light won't interact with light, you have to trick it by mixing it with matter. They built a nanoscale photonic cavity. Imagine two microscopic mirrors facing each other, trapping a photon bouncing millions of times a second. Right in the middle of that mirrored box, they placed an incredibly thin 2D sheet of semiconductor material. The trapped photon hits the semiconductor, an electron swallows it, gets excited, drops back down, and instantly spits the photon back out. Bouncing, swallowed, spat out. It happens so fast that the universe blurs the line. They lose their individual identities. They merge into a completely new hybrid quasi-particle, half light and half matter. It's called an exciton-polariton. It's the holy grail of computing. It travels blazingly fast like light, but because it's half matter, it has an electrical charge. And because they have a charge, if you put two of them together, they bump into each other. They solved the flashlight problem. They basically dressed the light up in an electron costume, so it could finally talk to the other light and do math. They demonstrated all optical nonlinear switching, the fundamental building block of an AI processor, without converting back to electricity. This feels like a textbook needs rewriting. But the craziest part is the energy. They did this using exactly 4 femtojoules of energy. What is a femtojoule? For context, lifting a medium-sized apple over your head takes about 1 joule of energy. A femtojoule is 1 quadrillionth of a joule, an amount of energy so microscopically small it barely exists in human terms. Compared to a standard transistor, this is orders of magnitude more efficient. The thermal loss is basically a rounding error, 0 heat. And the speed? The switch flips in a few picoseconds, 1 trillionth of a second. Even light itself, traveling at the maximum speed limit of the universe, only moves 1/3 of a millimeter in 1 picosecond. When you combine quadrillionths of a joule with trillionths of a second, you completely shatter the limitations of silicon chips. You eliminate the traffic jam. You eliminate the heat entirely. You are computing data literally at the speed of light. What does this mean for AI? It changes everything. You won't need to send your data to a massive cloud server farm anymore. You could run massive, trillion-parameter AI models locally, on your laptop, in your car, directly inside medical scanners. Imagine an autonomous vehicle making split-second decisions with 0 latency using the battery power of a digital watch. It solves the energy crisis, and it saves Moore's law. The electron took us as far as it could, but light takes us further. By creating this Frankenstein particle, physicists didn't just build a better switch, they built a bridge to the next era of human computing. We are officially leaving the electronic age. Welcome to the dawn of the photonic age. And honestly, I for one will welcome a laptop charger that doesn't give me third-degree burns. Just hold on, the photons are coming. Subscribe, leave a comment if your mind was properly blown today, and we'll see you next week on The Static Frontier. If you enjoyed this, we've turned it into a full podcast. Search for The Static Frontier on Apple Podcasts, Spotify, or wherever you listen. New episodes drop every week exploring the tech and science mysteries you never knew existed.